Section 4.5 deals with the relationship between centripetal acceleration and tangential acceleration. So let's look at it this way. Tangential and more generally radial acceleration. We just talked about centripetal acceleration, and that's a form of radial acceleration. So let's see what we're talking about. If I have a circle, here's my radius, and I've got some point on the surface moving. And in order to have a tangential acceleration, then we're not moving at constant speed, right? So we're outside of uniform circular motion right now. So let's give it some acceleration going around the circle, right? So I don't even want to draw it as an arrow because that looks like a vector. I'm going to draw it as a curve, right? We're accelerating around the circle. Right, so you just started your car and the engine's at a different speed, right? The speed of the engine is changing, or you just started moving in your car and the tires are moving at a different speed. All right, so we can talk about the instantaneous centripetal acceleration. And we talked about last time, that's just v squared over r for the instantaneous velocity. And which direction does that point? That points towards the center, right? Well, the radial direction we would usually say is outward. In general, you can choose your own coordinate systems. This is just the standard, right? So your radial acceleration in this case is minus AC because it's pointed towards the center. So what about that acceleration that's tangential? Well, that's what's actually changing the speed of it, right? We said we're no longer in uniform circular motion, so the speed is changing. As well as the direction. And that is the impact of what we'll call AT, the tangential acceleration. So let's imagine the kind of cases where this is important. You've got a car driving over a hill. How fast can that car go before it jumps off the hill? Well, we don't have the force background yet to solve something like that, but we can imagine what's happening when the car's at the top of the hill. We'll be able to calculate that kind of thing eventually. For our first case, let's just say we're moving at constant speed. What does the acceleration on that car look like? Well, we're going to model the hill as a circle, right? There's some radius of curvature associated to this hill. So in order for it to stay on the ground, we need that centripetal acceleration to keep it moving in a circle. If the car is speeding up, well, let's say that we have a tangential acceleration now, then you also have to consider that. So if you want the total acceleration, it's the vector sum of the centripetal and the tangential, but we already talked about this. These are perpendicular. So when we add two perpendicular vectors, we can get that the magnitude of A then is the square root of the sum of the squares. Right? Because we know they're perpendicular, we have an easy way to find the magnitude. We'll do some problems like this. Like I said in the last video, we'll do this far more once we have access to forces. I just want to look at a roller coaster track here, and we can consider, curvature of this part and the curvature of this part. And think about what direction our accelerations are. So if we're moving along this track and we're, do I want to be accelerating? Let's say that we have a constant tangential acceleration. So if I look at this point, I've got my constant tangential acceleration in this direction. Which way is my centripetal acceleration? It has to be towards the center. And we get a total acceleration, something like this. Over here, we'll have the same kind of situation. I can have my constant tangential acceleration, and now my radial acceleration will be towards the center of this circle. And we end up with a total acceleration that looks like this. So we can see how it changes based on the shape of the path, right? And how we can model that using the circular parts and the curvature, the radius of curvature. All right, so we will return this with some specific examples later. For now, we're just introducing this model.